Welcome to our video on Gaussian elimination and Gauss-Jordan elimination. These are powerful methods for solving systems of linear equations, which are fundamental in mathematics, engineering, physics, economics, and many other fields. Let's start by understanding what a system of linear equations is. A system of linear equations is a collection of two or more linear equations, each involving the same set of variables. We typically denote these variables as x1, x2, and so on. This system can also be represented in matrix form as a times x equals b, where A is the coefficient matrix, x is the vector of variables, and b is the vector of constants on the right-hand side. For our demonstration, let's consider a specific example of a system with three equations and three unknowns. Here we have x plus 2y plus c equals 6, 2x plus 3y plus 3z equals 14, and x plus y plus c equals 8. The first step in both Gaussian and Gauss-Jordan elimination is to represent our system using an augmented matrix. An augmented matrix combines the coefficient matrix A with the constant vector B, separated by a vertical line. For our example, the augmented matrix looks like this. To solve this system, we'll use elementary row operations. There are three types. First, we can swap any two rows. Second, we can multiply a row by a non-zero scalar. And third, we can add or subtract a multiple of one row from another row. Our goal is to transform the matrix into a simpler form where the solution is easy to read. Now, let's perform Gaussian elimination, which transforms our matrix into row-echelon form. A matrix is in row-echelon form when, first, all rows consisting entirely of zeros are at the bottom. Second, the leading entry of each non-zero row is to the right of the leading entry of the row above it. And third, all entries in a column below a leading entry are zeros. Let's begin the process with our augmented matrix. Our first goal is to create zeros in the first column below the first entry. We'll subtract twice row 1 from row 2. This gives us 0 times x plus negative 1, y plus 1z equals 2 for our new row 2. Next, we'll subtract row 1 from row 3. Giving us 0 times x minus 1y plus 0z equals 2 for our new row 3. Now, let's focus on the second column. We need to create a 0 in the third row beneath the second row's leading entry. Since both the second and third rows have negative 1 in the second column, we can simply subtract row 2 from row 3. This gives us 0 times x plus 0, y minus 1z equals 0 for our new row 3. Great! We've now reached row-echelon form. Notice that all entries below each leading entry are zeros, and the leading entries move to the right as we go down the rows. This is the goal of Gaussian elimination. Now we can solve the system through back substitution. From the third row, we can directly see that negative z equals 0, so z equals 0. Looking at the second row, we have negative y plus z equals 2. Since we know z equals 0, we get negative y equals 2, so y equals negative 2. Finally, from the first row, we have x plus 2, y plus z equals 6. Substituting y equals negative 2 and z equals 0, we get x plus 2 times negative 2 plus 0 equals 6, which simplifies to x minus 4 equals 6, giving us x equals 10. Now, let's explore Gauss-Jordan elimination, which extends Gaussian elimination to convert the matrix into reduced row-echelon form. In reduced row-echelon form, first, the matrix is in row-echelon form. Second, every leading entry is equal to 1. And third, each leading one is the only non-zero entry in its column. Let's continue from where we left off with our matrix in row-echelon form. First, we'll make the leading entry in the third row equal to 1. We multiply row 3 by negative 1, which gives us z equals 0. Next, we make the leading entry in the second row equal to 1 by multiplying row 2 by negative 1. This gives us y minus z equals negative 2, or simplified, y equals negative 2 since z is 0. Now, we eliminate non-zero entries above each leading one. For the third column, we subtract row 3 from row 2, giving us y equals negative 2. Then, we subtract row 2 from row 1 and subtract 1 times row 3 from row 1, which gives us x equals 10. Now, our matrix is in reduced row-echelon form. The beauty of Gauss-Jordan elimination is that we can directly read the solution from the matrix without needing back substitution. From our reduced row-echelon form, we can clearly see that x equals 10, y equals -2, and z equals 0. This matches the solution we found earlier using Gaussian elimination and back substitution. Let's compare Gaussian and Gauss-Jordan elimination. Gaussian elimination transforms the matrix to row-echelon form and requires back substitution to find the solution. Gauss-Jordan elimination transforms the matrix to reduced row-echelon form, allowing the solution to be read directly. Both methods are powerful tools for solving systems of linear equations, and the choice between them often depends on the specific application and computational efficiency needed. In this video, we've walked through both methods step by step, showing how they can be used to solve the same system of linear equations. Thank you for watching. I hope this video has helped you understand Gaussian and Gauss-Jordan elimination for solving systems of linear equations.